Okay, 2.4 is talk about parent functions. Those are the very most uh, fundamental functions that we need to know. Um, all the other functions are built upon those functions, and they're called parent functions. So all the other functions emerge from those functions. So we're going to talk about these functions specifically, one by one. So let's talk about the linear and the squaring functions first. Uh, okay, so we know a linear function gives you a straight line when you plot on the graph. And sometimes we are required to write down or find the equation of a line with some given conditions, like in the following example. We want to write a linear function f for which f1 equal to 3 and f4 equal to 0. Okay, so these are given 2 points on the line. We can call these 2 points x1, y1, x2, 2, where x1 equal to 1 and y1 equal to 3. Okay, so you should be able to read the information from the problem itself. And x2 equal to 0 and the y2 equal to 4. I mean, x2 equal to 4 and the y2 equal to 0, right? So then we can use the slope formula to find the slope of the line using the 2 points. So just take the quotient of y2 minus y1, x2 minus x1. So we got 0 minus 3 over 4 minus 1. And 0 minus 3 is just negative 3, and 4 minus 1 is 3. So we get the negative 3, which is negative 1. So that's the slope. And then we can use the point slope form to write down the equation of the line. Y minus 1 equal to m times x minus x1. So just plug in those numbers. So we get y minus 3, which is y1, equal to negative 1, which is m, which is a font. X minus 1, 1 is the x1. Okay, and then you just simplify it a little bit. On the right side, if you distribute negative 1, you get the negative x plus 1. Okay, and then you move 3 to the right and then simplify. So it becomes plus 3 on the right. So we got y equal to negative x plus 4. 1 plus 3 is 4. So that's the equation of the line. All right, shown in the graph. Any questions for this example? Nope. And the next thing is called the linear and the squaring functions. We, had some have some special examples of linear functions. For example, the constant function f(x) equal to c. That's also a linear function. It gives a horizontal line passing through c on the y-axis. Okay, or the y-intercept is c. So that's a linear function. And then we got identity function, f of x equal to x. Okay, so or y equal to x. So that's a straight line passing through the origin with a slope 1, identity function, because y is equal to x. Okay, so these are two special cases of linear functions. But then square function, f of x equal to x squared, that's also called the parabola, right? Quadratic function. Okay, so that's a special case of quadratic function. And then we got the cubic, square root, and the reciprocal functions. Okay, it's a cubic function f of x equal to x cubed. So if you draw the graph, you get something like this. It goes up on the right and it goes on the left, and also passes through the origin. So that's cubic function. And the square root function is defined as f(x) equal to square root x. Okay, so if you plot the graph, you get the only the curve in the first quadrant. Okay, That's the whole curve for the function. It goes up, you know, uh, increases, right? And then we got the reciprocal function f of x equal to 1 of x. Okay, so you take the reciprocal of x. So if you graph the function, you get two branches, one in the first quadrant and the other in the third quadrant. And both x and y axis are the asymptotes for the curves. All right. So this is the shape of the reciprocal function. So we just plot the graph of those functions so that you have some idea, have some image on how the curves look like. All right. Now the step when the piecewise functions or a spatial type of function. Okay. I don't know if we discussed this example before or not. Okay, we have piecewise defined function. I think we discussed the piecewise defined functions last time or even before. And step function is a spatial case of piecewise defined functions. So this time the function has many pieces. It's not just the 2 or 3 pieces. It has infinitely many pieces. And each piece, it just covers um, one unit on the x-axis. And if you plot the graph of the function, it's like a step, like a stage or whatever. So how is it defined? The step function is defined as the greatest integer less than or equal to x. So this is a little confusing, and I will explain a little bit from the graph. And so it's denoted by the x sandwiched by this notation. All right. It sometimes is called floor functions or some other names. But when you graph this function, you're going to get the horizontal pieces for each unit of x. So it's like a step or a stage as you go from left to the right. You're going to get the a bunch of steps goes up. So it's defined as the greatest integer less than or equal to x, as I said before. So let's see how we can evaluate this function. So that's the important thing when you try to graph a function, especially the piecewise defined functions. You need to look at definition and then draw it piece by piece. So let's look at the piece from x equal to 0 to x equal to 1. Okay. So that's a special piece. So when x is greater than or equal to 0 but less than 1, according to the definition of the step function, y, which is fx, is the greatest integer less than or equal to x. Okay, but when x is between 0 and 1, what is the greatest integer less than or equal to x? That'll be 0, right? For example, when x is equal to 0.1, then the greatest integer less than or equal to 0.1 is 0, right? Or x equal to 0.5, the greatest integer less than or equal to 0.5 is 0 also. Or when x equal to 0.9, then the greatest integer less than or equal to 0.9 is 0 also. So when you pick up x values from 0 to 1, you get all the function values equal to 0. So you just got a horizontal line on the x-axis from 0 to 1. Okay. But when x is equal to 1, then what happens? Then the greatest integer less than or equal to 1 is just 1, right? So it jumps, to 1. The x equal to 1. The y value, the function value jumps to 1 when x is equal to 1. So you got a jump there. And then when x is between 1 and 2, greater than equal to 1, less than 2, like 1.1, then the greatest integer less than or equal to 1.1 is 1, isn't it? So that's again 1, y equal to 1 again. When x equals 1.5, then the greatest integer less than or equal to 1.5 is also 1. So you get a y value equal to 1 again, x equal to 1.5. When x equal to 1.9, then the greatest integer less than or equal to 1.9 is 1 again, right? So when x is between 1 and 2, including 1 but not including 2, then the function value y is always 1. So we get another stage in here at y equal to 1 for x greater than equal to 1 and less than 2, right? So every time when you meet integer for x, it jumps 1 unit up on the right. So if you plot the whole graph of the function, you get all the steps like this. So that's called a step function, and that's why. All right. So we for each piece or each step, the left hand side is close to zero because as we just discussed, the left point is always included on the piece. But on the right side, we have an open circle for each piece because it jumps up 1 unit at that point. Okay, right? So the right hand side, the point for each piece is not included in the piece. So that's the step function, a very special function. Okay, it is a function. Okay, by the way, when you use the vertical line test, you draw any vertical line and see how many points and the line intersects with the curve or graph. You only get 1. So it is indeed a function, right? So that's the step function. Okay, just give you some idea about some bizarre things. Okay, so let's just do some algebra with the step function. How do you evaluate function f of x equal to the step function of x plus 2 when x equal to -3/2, 1, and -5/2? This time it's not exactly the step function. It's a little shifting, okay, in the x-axis, if you still remember. So what you do, you just plug in the values of x in the function and find out what it gives you. So f of -3/2, we plug in 3/2 for x. In the function, we got -3/2 plus 2 inside the bracket. So -3/2 plus 2 is just 1/2 if you write or rewrite 2 as 4 over 2. Okay, and then negative 3 plus 4, which is 1, we got 1 over 2. So we need to find the greatest integer less than or equal to 1/2, and that's just 0. The greatest integer less than or equal to half is 0, right? So f of negative 3 over 2 is just 0. Okay, so you cannot use the previous step function, to give out the answer. You need to evaluate in this particular um, variation of the step function. So how about f1? This time you just add 1 or 2 inside, you get 3. So we need to find the greatest integer less than or equal to 3, which is 3 itself. So f1 equal to 3. All right. Finally, f of negative 5 over 2, plug in x equal to negative 5 over 2, we get negative 5 over 2 plus 2. Again, you rewrite 2 as 4 over 2, so we get the negative 5 plus 4 on the top, which is negative 1, and the 2 at the bottom. So that gives you a negative 1/2 inside. And then you need to find the greatest integer less than or equal to negative 1/2. And that turns out to be negative 1. It's not 0. Okay, 0 is greater than negative 1/2. You need to find the greatest integer less than or equal to negative 1/2. Okay, you need to find the integer less than or equal to negative 1/2, but the greatest integer for that, right? So that's how you evaluate the piecewise defined function. Be very careful. Okay. So that's the step function and this evaluation. Okay. One of the difficult part for piecewise defined functions is to graph it. I think we talked about this before, but let's just do one more example of graphing of piecewise defined functions. So in this example, when you sketch the graph of the function f of x equal to 2x power 3 for x less than or equal to 1, and f of x equal to negative x plus 4 for x greater than 1. All right. So we've got two pieces. So you need to consider piece by piece. One piece on the left and the other piece on the right, and the boundary of the two pieces is x equal to 1, right? So one piece on the left, is for x less than or equal to 1. The other piece on the right is for x greater than 1, right? So when x is less than or equal to 1, so the left-hand side piece has the expression of f of x equal to x plus 3. So that's a linear function with slope 2 and y-intercept 3. Okay. So if you do that, you're going to get the half of the line on the left. And again, you should stop at the point of x equal to 1 for that piece, and erase the part of the line on the right. So you only get the half piece on the left for that line, but you do have a closed circle at x equal to 1 because at x equal to 1 the function is defined based on that expression. Okay, so the boundary point is included on the left hand side piece. And then we got another piece on the right and defined as f(x) equal to negative x plus 4. So this is another line with the slope negative 1 and y-intercept 4. So if you draw a line, you can get a piece for the right. Okay, you need to erase the other half piece of the line on the left. So it really actually doesn't go beyond the x equal to 1 to the left. So it does not intersect. It does not intersect with the y-axis, right? Because it's valid only for x greater than 1. So you should erase a piece of this line at the left of x equal to 1. So if you do that, you're going to get the half line on the right like this, showing the graph. And also the endpoints at the boundary at x equal to 1 is not defined by this expression. So we should put the open circle at the boundary or the left side of this half line. All right, so then the graph of this function is just two pieces, you know. And it is indeed a function if you draw vertical lines, you know, you see there's only one intersection of the curve of the graph with the with any vertical line, right? So that's how you draw piecewise defined functions. You know, sometimes this is a little tricky, and you be very careful about this. Okay, how do you start? You know, you need to follow the standard procedure. Okay, do it step by step. Don't rush. All right. Any questions about piecewise defined functions? No. And then why don't we just go to the next page? And this function is also a piecewise defined function, although in the original expression it doesn't say that. And this function is called the absolute value function. And it's defined as f of x equal to absolute value of x. Now we got different values when you take the absolute value of a function for negative numbers and the positive numbers of the variable x. Okay, and the rule, in other words, is different for the variable x to be negative or positive in the function. So, for example, when x is positive, okay, you know, just look at the bottom part. You know, when x is positive, then when you take the absolute value of x, you just get the number itself. So f of x equal to x for x greater than 0, right? Okay, but when x is negative, when you take the absolute value, you should get a positive number also. Okay, so then f of x equal to negative x in that case, because if you take the negative of a negative x, you get a positive number. So for example, f of a negative 1 is equal to 1, but you can also rewrite it as negative of negative 1 because we want to express the function in terms of x. Okay, but x is negative 1 in here, so we need to put another negative number in front of negative 1 to make it a positive 1, right? But when x equals negative 2, then in order to make the function value to be positive 2, which is the absolute value, we need to put a negative sign in front of negative 2. So that's why f of x equal to negative x for x less than or equal to 0, right? And then you just plot these two pieces separately, and time it becomes a little easier because we know these are just two straight lines, and on the left side we got the f of x equal to negative x or y equal to negative x. So that is a straight line passing through the origin, but with slope equal to -1. All right. So that is on the left side piece, x equal to 0. So that's the part of the curve on the left hand plane. Okay. And on the right side, the f(x) equal to x. So that's a line with a slope 1 passing through the origin. Okay. So we got the other piece on the right hand plane from the y-axis. So then if you, combine those pieces, you just get a V shape. So that's how the absolute value function looks like when you graph it. It's just a valley or V shape. Okay, so so these are some spatial functions, and then we can use those functions to build up the other functions. Okay. Any other questions? Any questions for this section? No question. Then why don't we just start another section, the next section 2.5. Okay. So let me upload the slides for 25. Okay, so what is 2.5? Okay, we might not be able to finish this section, but let's just start if you don't have any questions. So 2.5 is a little tricky. It's called transformations of functions. This is basically about graphing. So when you try to do all kinds of operations to the curve or the graph function, then you get another function. You can shift the graph function horizontally or vertically to get another function, or you can reflect the graph function to get another function. And then what's the relationship between those two functions? If you do that, how do you write down the expression of then the second function from the first function? Okay, so we're going to talk about the different types of operations. We call them symmetry operations. All right. So we're going to start from shifting graphs. So if you have the graph of y equal to fx given in the problem, then you can shift the graph of this function to get another function, but different ways. So you can do vertical and horizontal shifts. So what it says in here, vertical and horizontal shifts in the graph of y equal to fx are represented as follows. Okay, there are 4 different operations you can shift up, or you can shift down, you can shift to the right, or you can shift to the left. The graph of y equal to fx. So what you have to start is the graph of y equal to fx, and you try to shift it to get another function. So what's the expression of the other function after shifting from y equal to fx? Okay, so in the first case, if your work shifts the graph of y equal to fx c units up, Then you're going to get the graph of another function h, uh, which is f(x) plus c. So suppose c is a positive constant. Okay. So for example, h of x equal to f of x plus 1. It's just the graph of fx shifted upward by 1 unit if you graph h of x. Okay. Similarly, if you shifted the graph of y equal to x, f of x c down, then you're going to get the graph of h equal to f of x minus c, right? So that's pretty straight, but horizontal shifts are a little tricky. Okay, so horizontally shifts the graph of y equal to fx c units to the right. So if you shift the graph of y equal to fx c units to the right, what function do you get? You're going to get the function h of x, which is f of x minus c. Okay, when you shift to the right of fx, it's minus c, it's not plus c. All right, where c is a positive number here. Okay. Well, when you shift the graph of y equal to fx c units horizontally to the left, you're going to get the graph of h, which is f of x plus c. So again, c is the number here. Okay, so that's a little, that's contrary to what you might think. Okay, so horizontal shift, uh, you get x minus c here and to the right, and shift to the left, you get the x plus c. Okay, just remind you that. So it's the contrary to the case of vertical shifts. So keeping that in mind of this. Okay, let's do one example. So we got f of fx cubed shown on the left at the bottom. We just talked about those parent functions. So that's the cubic function. So we need to sketch the graph of the following two functions. H of x equal to x cubed plus 5. So you just add 5 to the function value. So you just shift the cubic function upward 5 units. Pretty simple. So in the middle, at the bottom of the graph. Okay, you get the curve like this. But how do you get a graph g equal to x minus cube minus q3 cube plus 2? So remember, if you compare g with f, given the problem, we got two things to do. We need to shift both horizontally and vertically. Okay, so you start from fx equal to x cubed, and you need to get a graph of g of x equal to x minus 3 cubed plus 2. So what you can do, you can shift horizontally first. So we got x minus 3 to the cube. So minus, right? So we need to shift to the right. Remember, when you shift horizontally, it's contrary to the case of a vertical shifting. So we need to shift the cubic function, the curve of cubic function, to the right 3 units to get x minus 3 to the cube, and then plus 2 to get the g. So that means we need to shift up 2 units from that to get a curve of a graph of g. So you see the graph on the right side at the bottom like this. So you shift the cubic function 3 units to the right first, and then 2 units up, right? Okay, so that's shifting. The next thing is called reflecting graphs. You can reflect the curve one function and get another function. So how can you write down the expression of the second function given the first function? Okay, so again, we got two cases in here. So you can reflect the curve either by the x-axis or by the y-axis. So reflections in the coordinate axis of the graph of y equal to f of x are represented as follows. Okay, so reflecting the graph of y equal to f of x in the x-axis. So if you reflect the graph of y equal to f of x by the x-axis, okay, you can get the graph of h. So you get another function, and function we call it h of x. It's just the negative of f of x, okay, because you are reflecting across the x-axis. So that's like a mirror of the horizontal plane if you put those two curves together, right? F and H. On the other hand, if you reflect the graph of y equal to fx in the y-axis, so you reflect fx across the y-axis. So you're going to get the graph of h equal to f of negative x. So you change the x into negative x in f. So this time, the two curves are symmetric with respect to the y-axis. So that's a mirror on the y-axis, right? So let's just do one example also. Okay. So we got the three curves in here, and the graph with the function a f of x equal to x to the fourth, which is the left graph in the page, is shown below on the left. Okay, so that's the given function, given curve. So if each of the graphs B and C next to it is a transformation of the graph of f, write the equation with each of these functions. Okay. So we're doing the opposite things from the first example. We are given the graph. We need to write down the equation of the graph. Okay. So you can see the graph in the middle can be treated as two steps from the first graph. So first, you move up the graph of f equal to x fourth up to units and then reflect across the x-axis, horizontally, horizontal plane. So you need to, so that means you can do what? Or you can reflect first there, then move up, right? You can reflect the first graph across the x-axis and then move up 2 units. So it just becomes what? So negative x to the fourth plus 2, right? So this function is just the g equal to negative x fourth plus 2, okay? Reflecting across the x-axis, you just put a negative sign to the whole thing. So that's negative x to the fourth. And you shift the 2 units up, so you plus 2. How about the other one on the right? So this time you reflect the curve to the lower plane. So that's across the curve, reflect the curve across the x-axis again, and then you shift the curve 3 units to the right. So you're going to get what? Negative of x to the fourth as the first step, and then you shift 2 units to the right, so it becomes x minus 3 to the fourth. So that's the negative of x minus 3 to the fourth, and we call it h, isn't it? Okay. So you have to do this step by step. Okay. Does it make sense? So you get the negative of x to the fourth when you reflect across the x-axis. And then you move 3 units to the right. So x becomes x minus 3. So at the end, you get the function h equals negative of x minus 3 to the fourth. Okay, so that's how you do it. So we didn't finish with this section today. We're going to do it on Friday again. So remember to take the quiz by yourself on Wednesday from 1 to 1:15. We don't have class on Wednesday, and we'll meet you again on Friday. But make sure you make up quiz tests and also the homework. Don't forget about homework, and send requests for extension in WebSign if you missed deadline for homework. Okay, so let me just stop the recording now.